Thank you. Hello. Thank you for having me. Will AI help save us from ourselves? Or are we smart enough to figure it out without it? Well, we're really not doing too well as a civilization, are we? We can't figure out global warming. And we are set to exceed the Paris Accord limit of 1.5 degrees rise over pre-industrial times. And if we look beyond, the trends and commitments don't really line up. We are set for at least 2 degrees of global warming. So what can we do? How can we rebalance this dichotomy between advancing our civilization and preventing a climate catastrophe? Well, I mean, the answer everybody in this room knows. We have to increase the mix of renewable technologies that we can bring and scale into this world. We have to reduce carbon emissions from fossil fuels. And we have to look for transformative, revolutionary solutions. For example, nuclear fusion at industrial scale to create baseloads and things like that. And we believe that artificial intelligence has the power to be one of those transformative solutions. In fact, what I'd like to show you is some proof of that, some evidence of that. At PhysicsX, we do just that. We build and invent AI technologies to improve the efficiencies and the power generated by renewable machines, reduce power consumptions from automobiles and airplanes, to make medical devices feasible within the human body, to revolutionize the way material processing is and manufacturing endpoints are integrated into our engineering optimization process. So we can really go end to end from concept, ideation, design and development into manufacturing. And we do that by addressing the engineering process by itself using artificial intelligence. So I'll show you a bit about this. First, we're going back about 4 decades here on the left-hand side of this graph. And this is also the only equation I'm going to show. This is Navier-Stokes' equation, one of the Navier-Stokes equations, and these cannot be solved by hand. It's one of the millennium problems in mathematics. So what one does, about 3-4 decades ago, scientists and engineers figured out that they can solve these equations numerically by computer, by discretizing the space on which they're solved into many small mesh elements, millions of those, and tiny time steps to resolve the turbulence scales. Now, that's great, and over the last 3 decades, advances in computation have meant that we can simulate a whole airplane in about an hour or a few hours, and complex aerodynamics, complex structures, FAA, and so on. But it still takes hours. And it's computationally expensive in the sense that we need hundreds or thousands of CPUs to do that. Now, the question is, in this age of AI, can we draw an analogy to artificial intelligence, in particular deep learning? Can we train deep learning models on some of this data that we generate on the left-hand side to give us a highly accurate outcome, nearly as accurate prediction as the CFD did itself, but do so much faster? And we'll see the reason for much faster in a moment. And the answer is yes, we can do that. And we can do that a lot faster, about 10,000 times faster. And we exploit that speed to generate optimization that goes much deeper in extracting performance out of processes and designs. So let's dive into it, literally. This is an example of an artificial heart that's developed by a UK medtech company called Kalon Cardio. On the left, you can see this artificial heart. It sits in the left ventricle. And the objective is to make this pump more efficient and create less blood damage, because that means less complications after it has been transplanted. The way we do that is we set up CFD simulations, the traditional numerical solving, CAE, computer-aided engineering, covers CFD, FEA, and things like that. So we set up these simulations, and we generate about 100, 150 or so of these simulations. And in that process, already start the optimization of the geometries. Now, once we have created those simulations, we have a bunch of data. We have high-quality data. That data exists on geometries, each shape, and in the physics, pressure distributions, shear distributions, and things like that. We use that data to train a deep learning model. Now, what does that mean? Deep learning models, we heard a bunch about this already, are essentially large matrices, right? But more importantly, this isn't really a training that happens in the physical space, because that's quite inefficient. We train these in a higher dimensional space called latent space, where we can abstract the geometries and still represent the physics. And geometry and physics always have been coupled. We didn't invent this. Einstein was one of the first in gravitation to describe how mass distorts the geometry of space-time, and the curvature of space-time tells us how masses move, how planets orbit, how satellites orbit. In aerodynamics, the geometry of a wing determines the pressure distribution over the wing and the lift and drag of this wing. Or the spars and spans in a bridge determine, together with material properties, the strength of that bridge. So we can see this correlation between geometry and physics, and we encode this in a latent space. The answer is that this large physics model then on any given geometry can predict in about 0.2 of a second what in this case takes a CFD simulation about an hour and a half. And it does that to a very high correlation. Typically, we find correlations of around 95%, in some cases 99%, back to the validated ground truth, the CFD, which after all has been around for a number of decades. What do we do about geometry? Because we can infer on the geometry very quickly, can we generate geometry quickly? And the answer is yes. In fraction of seconds, we can generate geometries, and not even human-conceived geometries. These are geometries that the AI agent explores in the design space, generatively, changing the number of blades, changing the curvature of the plates, and whatever else it finds interesting, while sticking within the constraints of what has to fit inside this little heart pump. Now, if we put all of this together, right, we have the geometry creation, we have the fast physics interpretation, and we add an optimizer to complete a loop where we generate a geometry, inference the physics, optimize this, meaning that we take the output of the physics and use that to change the geometry again. And that whole loop runs in about a second. This is real time on one GPU. Remember, 1 point of these 50 points takes over an hour in CFD. So within a minute here, we've achieved about 1% in performance improvement of this pump, delta P, which is proportional to flow. And in the background, we've also optimized for shear damage, for blood damage. That's a multi-objective optimization that happens, but here we're just looking at one graph. And in fact, we can add more physics into this. We have added physics like structures, for example, structure information. So we can inference on both fluid flow and structure and optimize for that. So multi-physics optimization. So there's a lot wrapped up into this, but it gives you an idea of how this process runs and how we extract value out of this. How do we use this in an engineering process? How do we even get these models? Well, first of all, we generate the CFD data, as I said before. That's the gray dots that you can see on the screen barely. And that's about 150 runs or so, and that takes about 2 weeks to generate. We train our model, as I described a little bit earlier. And what you see in the blue dots here is the model itself, the large physics model, running for about 2 days, generating 200,000 optimizations rather than 150 in 2 weeks. Now you can see that from the CFD runs, there's faint sort of gray line, which is the performance boundary of where we got to with CFD in those 2 weeks. Now those blue dots, the LPM model, right, also creates its own performance boundary here that you can see. But that's not a boundary we imposed. It can't go further. And the reason is there's just no better design. It has found all the designs that could possibly generate better performance along these contours of better blood flow and better or lower blood damage. This means there is no better design within the constraints of that. We have found the limits of the physically possible, which is pretty cool. And now a designer can choose and balance between blood flow and blood damage. Now, is our model hallucinating? Is this imagination? Or is this real? Well, we know how to answer that question because each one of these points is a geometry, right? We take the best geometry and we just stick it back into the CFD. It's a geometry. We can remesh it, run the CFD, and see what is the result. What's the blood damage? What's the blood flow? And the outcome is that is quite accurately represented by the LPM. Usually we see a few percent differences. And where we don't, we just generate a little bit more data to retrain the model and revalidate it. So we have a way of getting back to the ground truth to make sure it's real, it's high quality. Now, does this work in other contexts? And the answer is yes. We've gone from the heart pump, the size of your thumb, to a hydro turbine the size of a small house. And here we've extracted a performance increase that was about 4 years' worth of development just by optimizing geometry, which is essentially free. Costs the same to manufacture this. So that's incredible value. We've also done this for wind turbines. We've applied this to wind turbines. One of those use cases was where we predicted the overheating of wind turbines over a whole year worth of wind conditions. Again, which would take a long time to simulate, and here it takes about a second or so. This means we can configure wind turbines in a way so they don't overheat and don't have to reduce their power output as a result of that. We are now working on applying this to wind farms at scale. When wind farms are built, you have to decide where to place the wind turbines. And oftentimes, you can't do this by simulation. If that wind farm is 20 wind turbines or more, it will take a year to simulate that on a supercomputer just to optimize those paths and configurations of wind turbines. That can't be done. So we train a deep learning model on the physics of wind farms. And in much shorter amount of time, we can optimize that. Now, the value that can be produced here is staggering. It is estimated there's about 15% of wake losses in wind farms. So there's a potential of 15% more energy production from the wind turbines that we already have, just by placing them more intelligently. We've applied this to automobiles, to cooling flows, and in this case, for example, this was translated into a material cost reduction that was worth a few $1 million. We've applied this to noise prediction from helicopters. You see a pressure distribution changing across a helicopter blade. And the reason this is important is because in some jurisdictions, you have limits over what noise you can generate over cities. And so with this real-time solution, a pilot can plan their flight path and minimize the noise impact that residents experience. Now, it's interesting because you can see this going around, right? And we're changing pressures and all that. So the LPM can predict this at the speed that this blade is going around. But not in this video, but in real life. As fast as a real helicopter blade, which you can't even see. Yeah, goes around 400 RPM, and that thing predicts in about 1/10 of a second. So that's pretty staggering, isn't it? When it usually takes hours. We're exploring more difficult concepts around highly turbulent and time-varying regimes. You see an aerospace example up there. And we go all the way to a manufacturing endpoint. There's an example of an additive heat exchanger for a jet engine, which we've developed, and there are some structural resonance shapes of this heat exchanger that you can see in sort of a full end-to-end process from ideation, geometry, all the way to manufacturing. So just in summary here, a few points. I think this transformation I spoke to earlier, remember a few decades ago, we went from physical to virtual simulation, or CAE. We have a new transformation from CAE to AIE, from computer-aided engineering to artificially intelligence-assisted engineering. Now, this isn't going to take 3 decades. This is going to take a few years. A handful of years at most, too, because of the value that is at hand and the technology that exists already and that we can scale. So we know that engineering, as we understand it today, will change. And that's a good thing. because that is what will enable us to meet the challenges of tomorrow, like improving the efficiencies of renewable machines and reducing energy consumption of our products to meet the challenges we have. Thank you.